Good morning. My name is João Abrantes, and I'm part of a team with Professor Silva and Dr. Nuno Almeida. This team is integrated in the project CADFacts, and it's exploring a modular approach for deployment and testing of cardiac image processing and analysis methods in the clinical workflow. According to the World Health Organization, cardiovascular diseases are the cause of death of 32% of death causes worldwide, and it is estimated that almost 18 million people die annually from cardiac-related diseases. It is a main priority to continuously improve the capabilities of clinical diagnosis for an earlier detection of CVDs, which results in a higher rate of success on the treatment of a cardiac patient. Technological innovation and advancement in medical imaging led and continues to open doors for a better software-assisted diagnostic solutions, making them more precise, efficient, and non-invasive. The arrival of cardiac computerized tomography allowed the visualization of a three-dimensional volume of the human heart and provided a large volume of anatomical and functional data, which led to the development of a number of technologies and methodologies for cardiac analysis and diagnosis. For example, coronary computed tomography angiography is used for detecting the presence and severity of cardiac artery disease, also known as CAD, or myocardial CT perfusion, which evaluates and calculates quantitative values of the functionality of the myocardium perfusion. With any of these type of exams, there are a few steps and tools that compose a common workflow of the clinicians, and that workflow is depicted by our diagram. So data is acquired from the CT exam and is automatically stored in the PACS server, which is connected to the viewer, where a clinician can browse patients and associated studies. By selecting one study, the viewer will load the CT image from the PACS server. Then the clinician can adjust the viewing configuration to position different viewing planes to obtain the best possible orientation to examine, for example, the left ventricle. To improve viewing, the ways the pixels are displayed can be adjusted to enhance ranges of intensity, for example, highlighting the contrast in blood. And at this point, the clinician can take measures of particular structures of interest or apply any processing to extract notable information, like computing the amount of blood inside the left ventricle over time. Although imaging technologies have drastically improved, the current clinical support software systems are still far from harnessing their full potential. There is a large volume of work regarding the research of better and more advanced techniques, but the validation and deployment of these methods still faces some challenges. There's a large volume of data acquired by CT, and it leads to processing and analysis methods that require a large amount of computational resources. The deployment of these methods to be reviewed and validated by clinicians face some obstacles created by the existing cardiac workstations, which are mostly proprietary, not allowing an easy integration for the new solutions. These aspects create barriers for a more optimal and efficient process of exploration, testing, and validation. Developers often need to create a base platform that provides the full set of basic features aligned with the current clinical workflow, and obtaining feedback from clinicians is possible, but made harder and less informing, given that these novel systems are not integrated in their workflow, which entails a limited amount of data to be considered for testing. CADFacts team is proposing novel ways to assess coronary artery function through numerical simulation, and considering the challenges identified previously, this work aims to explore a modular solution for clinical CT imaging processing that could serve the design and test of these novel methods. This should provide the grounds that would facilitate their deployment and exploration by the clinicians towards a more adequate setting to profit from their insights. Overall, to meet the requirements of the system envisioned by the previous problems, the following goals are identified: gathering knowledge regarding recent trends in cardiac imaging and diagnosis, regarding current methods and approaches, understanding of the research and clinical workflow associated with cardiac diagnosis based on cardiac CT, and the definition of the main users and scenarios that will lead to the definition of requirements to support these users and these scenarios. The exploration of different possibilities to address requirements and propose the system architecture. And from this step, the development process started of the development of core models and of a proof of concept design, which supports the different stages of the cardiac analysis and workflow. In the first stage, we considered personas for defining the target users. Within this project's context, it is clear that there are two different types of end users. From one side, there are the clinicians, which will use this software for the current state-of-the-art workflow of medical imaging, and the researcher whose main goal is to create, test, and validate new methodologies. These personas are assumedly a first approach to facilitate a better understanding of the users and their characteristics, and are based on profile of actual researchers involved in this topic. Speaking about the two personas, we have João Melo with 32 years old. She is a clinician. She needs to visualize and annotate and analyze medical images. And she's looking for a DICOM viewer with the necessary tools and a familiar workflow for the post-examination imaging analysis. On the other side, we have Ricardo Pereira. He's 29 years old. He's a clinical researcher. He is developing and testing, and testing new calculations over cardiac CT, and he wants to create and test new cardiac CT methodologies using the most appropriate tools and not being dependent on the system's limitations. So for the researcher scenario, this scenario from the researcher is intertwined with the clinical with the clinician, one of the clinician scenario. So from the point of view of Ricardo, that is developing a new method to extract the coronary tree from CT images. He starts the development of this method in his preferred programming language. Then he deploys this novel method in a common platform with the clinician to be validated. Ricardo will wait for the feedback from the clinicians, where unfortunately some problems arose on his method on certain areas of the image. So Ricardo will open the image in question and browse for the image area which the clinician marked as problematic. Ricardo then endures some debugging and correction to correct the problems. And when he's satisfied, he will redeploy this new method in the common workflow, in the common platform for another iteration of the clinician's validation. From the side of Joanna, she will wait for the notification from Ricardo that the method is available. She will open the common platform and will trigger this new method. And during the execution of the method, she notices some incorrections in calculations in some areas of the image. So she will use annotation tools to highlight the region where the mistakes were happening, and will re-notify Ricardo that there's a problem. So after Ricardo's correction, she will then re-evaluate the method, and hopefully everything is okay and this method can be integrated in the system. Another scenario for the clinician is a more common workflow. In this case, the analysis of the left ventricular function from coronary CT angiography exam. She will open the system and browse from the exam she wants to analyze. She will adjust the viewing plane to isolate left ventricle. Then Joanna adjusts the window levels to highlight contrasts in the patient's blood. And then conditions are met for the measuring and analysis by the use of measuring and annotation tools. To support the vision described above, it is important that the proposed platform provides the clinician with a set of tools that are common to the cardiac workflow, and also having mobility as a main feature, because having personas archetype in mind, accessing exam images and data anywhere is highly useful. It's an highly useful feature which will improve the capabilities of co-working and cooperating with colleagues. It needs to include an access to a DICOM image archive for patients' data and images retrieval. It needs to include a user interface that will combine a number of essential features like image visualizer, window level adjustment, viewer layout customization for different image quadrants where different imaging planes are represented, and a post-examination report extraction where different type of clinical data can be compressed in a report format to be downloaded prior to the image analysis. Overall, it's important to note that the researchers will also profit from all the requirements identified for the clinician, since it will also provide them with ways of testing their methods inserted into the clinician's workflow. Additionally, from the researcher's perspective, the platform needs to enable different tools for developing novel methods and fast ways to deploy and update these methods. Since one major goal for the platform is to be extensible and dynamic, having a modular approach is paramount, since each component can be developed independently. And this is a major concern because it grants a higher consistency to the system as a whole. So if a new processing methodology is needed or developed and it needs to be tested, it can be easily added to the features faster by creating a new servers or modifying an existing one without major compromises with the whole project. Based on the modularity aspect reflected by the requirements definition, it was decided to explore solutions akin to a microkernel or a microservice software architecture, where the components are, when each component is independent of each other, or they interoperate with through an API, or in a case of a microkernel, the existence of a core system where each component acts as a plugin. The data storage service should work independently of the viewer, and more complex processing operations should be hosted in external services. This will remove any limitation in the language and framework that the image viewer might impose. This will make possible for someone to develop new processing units without the need to know how the core system works, creating an abstraction layer from this service to the core system. And so our system will consist of a PAC server for image storage, a DETI image viewer for the image visualization, and one or more image processing and data extraction services. It was decided to start with the image viewer since it will be the central component of the platform. And in this regard, we endured some research on selecting the approach to consider for the image viewer. At the onset of this task, we considered the work carried out to survey potential solutions, including options such as post-DICOM, Horus, Mango, DICOM Web Viewer, but based on the solution and requirements that we conceptualized, two deserve particular attention. In this case, it was WSIS and OHAF because they explore but with these ones, we explored overall features in a runtime. We analyzed the core code and we instantiated them for a more deep analysis. So with WSIS, the first open source project that was taken in consideration, it is a standalone and web-based DICOM viewer with a modular architecture. It is multi-language and has a flexible integration with various imaging information systems. This viewer allows high rendering with the OpenCV library. Its architecture is based on plugins, which are organized in plugin type bundles and are in form of Maven architects. However, since this project has little code level documentation and is organized as a Java enterprise project, it was found to have a steep learning curve to develop for the development process, making it a unrealistic solution for the time constraints of this project. The second and final open source viewer we tested was Open Health Imaging Foundation software, or HIF. It is designed to load large volumes of data in a short period of time and retrieving metadata and pixel data ahead of time. This is Cornerstone.js, that is a JavaScript library for visualization of medical images in web browsers. It works out of the box with image archives that support DICOM Web, provides a plugin framework, which are called extensions in this case, for creating task-based workflow modes, which can reuse the core functionalities. We found this solution more adequate for the needs of this project. It has an extensive documentation and several guidelines on the development process. It is a fully web-based application with an extensive open source development community with new features and extensions inside to be released and built to be extendable, adaptable, and customizable. We did that in mind. OHIF would be our viewer components that would be extended with the features required to integrate the external processing and analysis methods. Since OHIF has a flexible policy with which data archive to choose to interoperate with, we chose as PAC solution DCM4G ArcLight DICOM that is contains a web DICOM and is running in a Docker container connected to the Node.js application of the viewer. For the integration of external processing methods, and without loss of generality, it was created a Flask server which communicates with two novel OHIF extensions created by us that handles the transfer of data with the server. So the first extension that was created was the data selector and sender that filters data from the retrieved DICOM data to be sent to the imaging processor server. Another one is the display set builder that is responsible for receiving data from the processing server and to handle it and prepare it for the inspection of it in the viewer. Going a little bit deeper on each component, we have the PAC server, which is, as I said before, DCM4G DICOM archive. It's running in a Docker container. It was easily integrated with OHIF because OHIF has already a DICOM query retrieval component, which was configured to point to our PACs. Our extension that was created in the viewer for sending data to the processing server was the data selector and sender. Uses Cornerstone.js to extract the pixel data from the image that is being visualized to be loaded into a three-dimensional array. Then it's serialized into a JSON to be sent as a post request to the external processing server. It will be then waiting for the response, and then we'll call the next extension, the display set builder. The display set builder will be executed after a response from the post request of the previous extension, and is responsible for the deserialization of data received from the external server and loading this data to a three-dimensional structure, which will feed an image set that is an object in OHIF that is responsible for organizing image for visualization and listing. Our main model or external model was developed inside a Flask server, and it was developed as a small Python script that uses OpenCV to apply a Gaussian smoothing filter. The server receives a post request by the data selector and sender, will load the JSON objects and consumes a NumPy array with the data, which will then be processed by a Gaussian filter implemented in the OpenCV. After the processing is done, it feeds or it integrates the processed array. It will serialize the processed array and send back in the response to the viewer. This model represents a proof of concept of a remote service for image processing, which demonstrates the feasibility of our proposal of having external services not dependent of the central of the viewer, I wanted to say, which can operate as itself, and it can communicate with a central image viewer. So the work carried out demonstrates the suitability of the proposal of a system which is a modular solution which supports application and development of novel diagnosis techniques for cardiac CT, offers a shared environment between the researcher and the clinician, and creates a layer of abstraction from the researcher to the core system. The current stage of our proof of concept open routes for several advances in two main fronts. One is the OHIF viewer, which is in constant development, and so our application will profit from the advancements on the viewer. And this team is furthering exploring the development and integration of new functionalities by the integration of a semi-automated segmentation of the left ventricle, profile feature, which the same system could have different instances for different use cases, only sharing the most common tools. And another feature in site is the handling of non-pixel data for the processing outputs. Thank you so much.